In this example problem, we have a truss bridge with a load at point C pulling down on the truss system. The goal here is to figure out what forces are in each beam of this truss and whether they're in tension or compression. So when we start in a problem like this, what we have to understand is we're in static equilibrium, meaning everything is balanced. All the forces everywhere have to cancel out to zero since, as Newton's second law would say, if we're not accelerating, there's no net force. So what we end up having is a puzzle here where we start to break down what is happening at each point. So what we're going to do is look at each part of this truss, and we're going to break down each joint and identify what's happening at each spot. So we usually start with our points right here where the truss is actually attached. And at this point, we have reaction forces to this load. So we have a downward load. There's 200 pounds per block. I got 6 blocks. We have 1,200 pounds of downward load at position C. Well, that's got to be balanced somewhere else, right? So the where this truss is reacting would be at point A. We get an upward arrow, and that's going to be a value of 600. And at E, we would also have an equal 600 up. Now, we know this to be the case because that load is split and there's a symmetry there, whether it's evenly balanced. Now, there are trusses where that load would be off-centered. There might be a load like at some point here. And if that's the case, we would actually have to look at how that load would torque or cause a moment at those different pivot points. And we'd have to balance the moments first to identify that point A might actually be carrying more or less of the load than point E. But in this case, we have symmetry, and all the practice problems we're going to be working on moving forward will all have that kind of symmetry. All right, so what we know now, if we look at just position A, right, we have this upward force on the truss, and that's got to be balanced by these other two supports, right? So somehow we got to get a downward force that's equal in magnitude, right? So somewhere I must have a downward arrow that's also equal to 600 pounds, right? And the only truss support that can do that is this member A to B. So what I'm going to identify is that in order to get it to go downward, it's going to have to act along its truss member. So I'm going to draw a little arrow there, right? And when we look at vector arrows, for an arrow to point down and to the left, that's going to require force pieces left and down, right? And they have this grid here, which is really nice because it allows you to identify that this is actually a 200-pound piece of that force left and a 600 piece down, right? So you can see that AB acts left and down at that joint member. And when we look at the forces vertically, the 600 pounds now balance, but that 200 doesn't balance. And the way to balance that is going to be to have a force to the right of 200 pounds by joint AC. So that's going to identify that AC is pulling on that member to the right. So you have AB pushing down and to the left and joint AC pulling to the right. So what we can do here now, we've identified what's happening here. What we don't know is the actual force of this member, but if we do some trigonometry, we have two legs of a right triangle, the 200, the 600, and we can pull our calculator out and use Pythagorean theorem and say that 200 squared plus 600 squared, and then take the square root of that answer, and we'd find that that actual joint member is going to apply 632 pounds of force. That's the length of this member. That's going to be 632 pounds of force in that member, right? So now we've broken down what each of these members, AB and AC, are doing at that joint. Now let's zoom out, and now let's look at what's happening here at these other joints. So if A is pushing on that joint, we would say that it is in compression, right? And we would draw another arrow and say that since it's in compression, it's also pushing on that joint B, right? And since we know it's 632 pounds and it's being compressed, then we also know that this is 632 pounds. And if that's the case, then we know that it's got to act to the right with 200, just like we did before, and up with a total of 600, right? So those are the pieces of AB's impact at this joint right here, right? So we have this up and to the right, and we'll see what happens with BD and BC as well, right? So we're starting to piece together the way these forces are acting on this truss. Now, what we see here, we actually don't know which way BC acts. Does BC push on that joint, or does BC pull on that joint? Well, if we're getting an upward push from AB, then something has to be pulling down to balance that, right? So I'm going to draw this a little bit cleaner so you can see, right? If I take this force member that's acting up and to the right, we know that we have 600 pounds acting up. Well, something's got to act down. Well, BD acts left and right. Well, that means that this member has to be acting down and to the right. And so I can actually identify that BC must have an equal downward of 600. And based on its angle, oops, move this over a little bit, it's going to also have to have a rightward piece in order to align with where the truss is, right? And since it's 2 blocks, we know that this is 400 pounds and that down is 6, right? And so now if I'm looking at joint B here, we have 200 pounds acting right at B from AB. We have 400 pounds acting right on B from BC. Well, that 600 total pounds is going to have to get balanced by a force from BD of 600 pounds, right? So you start to see how everything balances out. The left and right pieces of it balance out. And so we get both the direction of the force and the amount. All right, so now we can start to continue to piece it together here. So if BD is pushing on that member, well, then we also get that same 600 acting at point D. All right, so we have this member acting that way and responding in kind here. This one's acting down and towards this joint, and so it's also going to pull on this joint C, right? And the amount of pulling is going to be equal to whatever this force is from B, and we can use Pythagorean theorem again. And this time we have a leg of 600, and we have a leg of 400 in BC. So if I take 600 squared and 400 squared and take the square root, I get 721 pounds as the force that's in BC, right? And that same 721 is going to have to act at point C, and it's going to have to act up and to the left. And so we're going to see that same symmetry. You're going to see an upward piece acting at C right here, and you're going to see a leftward piece for that same 721 to match up, right? So that's going to be the forces at C. Again, we can write in the same values. We got 400, we have 600, and oh, now let's look at C. Hey, we better have another 600 up. Well, it turns out, again, if you look at the symmetry here, you would see that this member must also pull up and to the right with the same amount, right? So we start seeing that same symmetry, which means this member is also 721 pounds, right? And it's going to pull down and to the left on that upper member. We know that if we're just looking back down here at this joint C, we're now starting to piece things together. Let's look at AC again. AC has 200 pounds that way. Well, that should be 200 pounds this way. And that's going to have to get balanced by 200 pounds to the right, which is then going to pull on this one with 200 pounds. All right, so we see that same symmetry. So if I'm labeling this member, we got 200 pounds here and 200 pounds here. I'm just filling in my blanks here. We have this member right here is 632 pounds. is member AB. If we zoom up, we know that this member we just found is 600 pounds. So we're starting to piece it all together. Now, you might guess that DE would have to be 632 pounds as well. You see the symmetry there. Well, and again, it would have to respond to this reaction force of 600 this way to react to the force at member E. And since CE is pulling left with 200, it's going to have to pull right at 200, right? And so we end up with a down and to the right from that member. And again, using the same geometry, it's going to be 632 pounds, right? And if it's down to the right, it's also up and to the left. And we should see that those forces are going to balance here as well. So that same 632, we see the same symmetry at point D that we see at point B. All right, so when we zoom out and we start filling in, there we go. All right, we now know that joint AB should have 632 pounds. AC we have is 200. BC is 721. BD we have is 600. CD is this up and to the right is also 721. CE is this bottom right member of 200. And DE is 632. Right? And when they say status, what they're asking for is whether it's in compression or tension. Right? So when you look at members here, they're either getting squeezed or they're being stretched. Right? So if those pins are squeezing it together, the actual member is going to have to be pushing out. Right? So here's a good little visual here. Right? This is a Star Wars scene where these characters are getting squeezed together. Right? They're getting compressed. And they're in turn pushing on the walls, right? So the arrows that we draw on the beams are what the beams are going to be doing to those pins. So since that pin is compressing those beams, we're going to see arrows pointing towards the pin as compression. And this is an example of a torture device where he's getting pulled, he's getting stretched, he would be in tension. And as a result, he's in turn pulling inward on the ropes that are attached to his arm. So it's a good little visual to think about tension and compression with beams. Right, so when we look at these arrow directions, right, we see that DE on the right is pushing out on the member, and that's as if it's getting squeezed. And so we would say that this is in compression when the arrows point out. And any arrows that point in would be pulling in on the members as if they're getting pulled away by that. And so we would get tension for a member like CD that has arrows pointing in. All right, so if I go through each member, we start with AB. We have arrows pushing out, so we would say compression. AC, we have arrows pulling in, so we're in tension. BC, we have arrows pulling in, it's in tension. We have BD, we have arrows pushing out, so it's being compressed. CD, we just said is compression. CE down at the bottom, it got arrows pulling in, so it's in tension. And DE, sorry, I think I did the wrong ones here. CD should be arrows pulling in sorry, should have tension in here. Misread the members. And DE we have in compression. All right, so we've broken down this whole truss now. We now know exactly how much force is being bared by each member, right? And if you're a bridge designer and you're trying to build a bridge and figure out how to support different loads, it's going to be important to do one of these static breakdowns to determine what your weakest link is, right? So you're going to be looking at, what the materials are made of, how thick they are, how much they can handle in compression and tension, and determine where your weak points are going to be, and then engineer around trying to make sure that structure is strong enough to support whatever loads you're going to handle. But here's a little simple breakdown of a nice symmetrical truss that walks you through how we can break down each individual point and look at the forces at that point alone and evaluate what forces must be in those beams.